So in summary, we've seen that we can write the velocity of a point at a position, let's say x plus dx, in terms of the velocity at a neighboring point x, plus a variation that looks like a Taylor series in terms of the step size dx and this tensor called the velocity gradient tensor. And so I've written out the velocity gradient tensor in matrix form here, just so that we can look at all of the different terms. And in component form, we might also write it in terms of individual elements that look like this. So at the beginning, we said that we could write any arbitrary deformation in terms of a translation plus a rotation and a deformation. So we can certainly see the idea of a translation, that it looks like if there was no deformation at all, then the velocity of the neighboring point would be exactly the same as the current point, which might be 0, or it might be a steady velocity moving through space. So everything else, our rotation and our deformation, must be wrapped up in this velocity gradient tensor. And we've seen what these individual elements look like as we go through. But the thing to remember is that we might well want to write this tensor grad v, which has 9 components, as seen here, is in general going to have 9 independent terms. We can also always write a tensor like this in terms of 2 components that would be a symmetric and an anti-symmetric tensor. And so we might write this by taking grad v. To make it symmetric, we just need to flip it about its diagonal. So we might write that as grad v transposed. And in general, people don't put parentheses around this, but we'll do it at least the first time, just to remember that we write the tensor and then we take the transpose of the tensor. And if I want to get this, then I can also combine that with a statement that looks like, let's say, take 1/2 of grad v minus grad v transposed. And so those two are identical ideas. This is a symmetric tensor. And so in general, since it's symmetric, it says that the items above and below the diagonal have to be the same as each other. So this has 6 independent terms. And then this is an anti-symmetric tensor. Which has at most 3 independent terms. Because along the diagonal, the only way a number can be equal to minus itself is going to be if those terms are 0. And so these terms are terms that we've already seen that we might be interested in thinking about for deformations. And so we've seen that we could write this in terms of a tensor that we might have called epsilon dot, which is a rate of straining tensor. And then this one would also be typically called a rotation rate tensor, or sometimes a vorticity tensor. And so this is the symmetric one that's to do with deformation. We see these halves here, and so not everybody will write this in terms of halves. You might also see this written as 1/2 of a tensor gamma dot. But it's exactly the same thing. It's just a matter of whether the half is in there. And so if we take that for this, we can think about making this tensor symmetric. And we've seen what these individual terms look like. So we'll see that the terms along the diagonal are to do with the rate of stretching. So we've seen that terms that look like epsilon dot alpha alpha correspond to linear rates of stretching, or what we've called extension. We've seen that the off-diagonal terms are associated with rotation of line elements. So the off-diagonal terms are to do with shearing. And finally, we've also seen the idea that if I take all of the diagonal terms together, so if I take this term and this term and this term and add them all together, then that we can write as the divergence of the velocity is equal to the trace of this velocity gradient tensor. and that's associated with volumetric rates of change, and so changes in material volume. So this would be volumetric changes. The final thing that we might note is to note that this antisymmetric tensor, if it only has 3 independent terms, then this tensor might be something that we actually don't even really need a tensor to describe. Because if there's only 3 independent terms, then we can actually write it as a vector. So if I was to write out this tensor omega, then we might write omega as an antisymmetric tensor. So it might have zeros along the diagonal, and only 3 non-zero terms. We can call them anything we like. I'm going to call this one omega 1. So to make it symmetric, this has to be minus omega 1. I've got to call this one omega 2. So to make it antisymmetric, this would be minus omega 2. And then finally, we'll call this one omega 3, and this one is minus omega 3. So that's an antisymmetric tensor. And it's a rotation rate tensor. And since it's only got 3 components, then we might want to express it in terms of a vector, which we'll call omega, which would have components omega 1, omega 2, and omega 3. And this is frequently called the vorticity tensor. And as an exercise, we can show that we can convert these two by a suitable multiplication. And that multiplication is in terms of a 3rd rank tensor, which is usually called epsilon, not epsilon dot, but it would be epsilon. It's a 3rd rank tensor that we might write like that. And if we were to write this out in component form, then we would say that omega ij is equal to we'll need a 1/2 in here, is equal to epsilon ijk times a dot product with omega k, where epsilon ijk is the alternating tensor, and so epsilon ijk is equal to 0 for I equal to j equal to k. Is equal to either +1 or -1, depending on how I, j, and k rotate. So if we go I to j to k, and they're not equal to each other, and we go clockwise, then it's equal to +1. If we go in a counterclockwise, so we have ikj or jik, then it will be equal to -1. And if we combine this and we multiply that out, we can relate this tensor, this antisymmetric tensor, with a simpler way of representing things in terms of a vorticity vector. Now, this might look quite confusing in terms of very general things. What we're going to do to look at this summary is we're going to break this down for 2 typical kinds of flows. The first one will be connected to the movie, deformation of a continuous medium, where we'll think about what John calls a rectilinear shear flow, and then we're going to think about a more complicated flow, flow past a sphere.